Greetings. Today, we uncover a secret that changed the course of World War II. A seemingly simple radio component revealing the staggering technological and industrial gap between America and Germany. Imagine a tiny quartz crystal, crafted with such precision that it could power an entire war effort. Yet behind this small element lies a revolution in manufacturing and military strategy. How could one crystal, produced in millions, embody a technological leap so vast that Germany's entire war machine seemed hopelessly outmatched? Could the difference in mass production, rather than battlefield tactics, have decided the outcome? And what secrets did captured American radios unveil about a society capable of turning industrial scale into battlefield dominance? In this video, we will trace how the United States' extraordinary capacity to produce reliable, advanced communication devices, massive quantities of crystal-controlled, modular, self-tuning radios, shattered German illusions of technological superiority. We'll explore how these innovations weren't just about better gear, but about transforming war into an industrial process, where victory belonged to those who could manufacture at scale, not just invent at the frontier. We promise to take you inside the secret labs and underground factories where German engineers, examining these American devices, realized that the future of warfare would be decided not just by soldiers or tactics, but by factories and mass production. The story you're about to hear will reveal how the seemingly modest radio crystal became a symbol of the Industrial Revolution in military history, an unassuming piece that tipped the balance of global conflict. The real battle, it turns out, had already begun long before the first shot was fired. It was fought in the assembly lines, in the laboratories, and in the minds of engineers shaping the future of war itself. Now, let's begin with the first chapter. On February 16, in the year 1943, echoes of a significant moment resonated through the quiet corridors of German military intelligence. It was on this day that the seemingly humble but crucial discovery was made, a moment that would ripple through the fabric of the conflict's course. Engineer Klaus Hermann, a seasoned expert of the Oberg unit, carried with him a delicate instrument, a screwdriver, that wavered ever so slightly in his grasp as he cautiously unlocked a sealed, military-issue metal case. This case contained a find of extraordinary importance, a fully intact American radio set, recently captured from the chaos of combat. Around him, 5 of Germany's most skilled and experienced radio engineers, each with years of training and a reputation for meticulous craftsmanship, leaned in with intense anticipation. They were eager to scrutinize the equipment meticulously, aware that this discovery held the potential to shed light on the technological capabilities of their enemies. The equipment had been seized during a fierce encounter at Casarine Pass, a strategic mountain corridor where recent battles had left behind remnants of American machinery. For nearly 3 long years, the German military had been fed a steady diet of dismissive propaganda from Berlin. The narrative insisted that American technology was outdated, cheap, and mass-produced for a nation of shopkeepers and assembly line workers. The reports from the American Radio Intelligence Service reinforced this notion. American communications, they claimed, relied on archaic equipment, primitive designs, and poorly trained operators, rendering them unreliable and easy to intercept. Confidence in superior German technology seemed unshakable, bolstered by these assertions. But as the case was carefully pried open, it became evident that everything they had believed might be wrong. Inside, they found an 508 Seychelles rupees radio set, a device explicitly designed for tank communication, along with an 510 Seychelles rupees receiver. Both pieces of equipment were remarkably preserved, left seemingly untouched by the destruction around them. The radios still contained their crystals, delicate oscillators that encode and decode signals, along with cables, and even a technical manual, all secured firmly in place within their specialized brackets. The scene was charged with significance. Sherman, along with his team, recognized immediately that they had stumbled upon a treasure trove of intelligence. Without hesitation, they ordered the equipment to be transported swiftly to the closest German testing facility, knowing that analyzing this piece of captured American technology could provide groundbreaking insights. The equipment was moved with utmost care to Technical Testing Station Number 12, arriving on the very afternoon of February 16. The significance of this event cannot be overstated. For the next 72 hours, these German engineers would immerse themselves in disassembling, testing, and understanding their discovery. What they uncovered would rapidly dismantle long-held beliefs and assumptions held by German military strategists. The initial analysis would reveal not just modest technological differences but expose an industrial disparity so profound that it cast doubt on Germany's prospects of victory in this war. Their differences extended beyond the mere technical specifics. They revealed a vast chasm in manufacturing capacity, design sophistication, and operational efficiency. As the engineers delved deeper into the equipment's workings, they realized that the implications went far beyond casual technical curiosity. Their examination would unravel truths about American industrial strength, about a nation capable of producing, in vast quantities, complex, reliable, and finely tuned communication devices. These devices embodied an industrial acumen and a capacity for mass production so advanced that the Germans would come to see that matching, let alone surpassing, such systems was all but impossible for their own industrial resources. The capture at Casarine Pass had been the culmination of a fierce and desperate engagement on the 14th of February. German forces under General Erwin Rommel engaged in a stubborn counterattack against less experienced American troops, managed to score a tactical victory that pushed the American Second Corps back by approximately 50 miles and rendered over 100 American tanks inoperable. This success, however, was only the beginning of what would become a turning point. In the chaos of that breakthrough, German technical intelligence teams, swiftly moving among the battlefield wreckage, began their search for any signs of the enemy's underlying capabilities. Among the debris, they found an abandoned Sherman tank, a piece of American armor whose turret had been shattered by a German 58mm gun, yet, miraculously, its radio compartment had survived the attack, intact and untouched by fire or shrapnel. Within that radio compartment, Friedrich Weber, a committed signals intelligence officer attached to the 21st Panzer Division, discovered not just one but two complete pieces of American radio equipment. The first was the 508 Seychelles rupees, designed specifically for tank-to-tank conversations, and the second was an 510 Seychelles rupees receiver, intended for broader signals reception. Both devices looked remarkably preserved, crystals, cables, and even the technical instructions, all still in place and seemingly ready for operation. Weber understood immediately that this was a discovery of immense importance. Without hesitation, he ordered that these valuable items be carefully packaged and hurriedly sent to the nearest German technical testing station for detailed analysis. The equipment arrived at Technical within a clandestine underground complex nestled beneath the bustling city of Tunis, an extraordinary facility operated, a hub of cutting-edge radio engineering, staffed by some of Germany's most talented specialists. This hidden laboratory was home to highly skilled engineers who had previously crafted and refined the very communication systems used by the Wehrmacht during the war. Among them was Oberingenieur Klaus Sherman, a former chief designer at Telefunken, a renowned German electronics firm, who now led the meticulous examination of these mysterious radio devices. Accompanying him was an elite team of experts, each specializing in different facets of radio technology, ranging from frequency synthesis and circuit architecture to manufacturing processes and signals intelligence, each brought together to uncover the secrets cloaked within these foreign-made radios. Their investigation began with a thorough exterior inspection. The American radios, they observed, were encased in heavy-duty steel housings painted an olive drab color, typical of military gear. Every seam and connection was sealed with rubber gaskets, designed to prevent infiltration by dust, water, or other environmental factors. Oberingenieur Herman made a detailed note in his initial report that the craftsmanship and durability of these housings surpassed anything he had previously encountered in their German military hardware. Such construction was meant to shield the sensitive internal components from harsh conditions, be it water intrusion, abrasive dust, shocks from rough terrain, or extreme fluctuations in temperature, circumstances that would be sure to incapacitate lesser equipment. However, it was the subsequent discovery upon opening the cases that truly stunned the team. Inside, they encountered a marvel of standardization and mass production, unlike anything typical for military radios they were accustomed to. All internal elements were modular, arranged uniformly, and designed for rapid and large-scale manufacturing. Instead of bespoke adjustments or finely tuned parts, each component adhered strictly to specifications found in the accompanying technical manuals. No manual tuning adjustments, no technician marks or customized wiring. This uniformity indicated that the radios were manufactured at enormous scale, meant to be assembled swiftly in factories across the continent by semi-skilled workers, rather than painstakingly assembled by highly trained technicians. Particularly intriguing was the meticulous quality and precision of the crystal units used within these devices. Leighton Hans Schreiber, a seasoned expert specializing in frequency control, scrutinized the crystals that set the operational frequencies of the radios. He initially anticipated that the crystals would be ordinary, perhaps recycled civilian components, simple and inexpensive. Instead, he discovered precision quartz crystal oscillators each crafted to extraordinary tolerances measured in parts per million, a level of accuracy requiring weeks of dedicated laboratory work in Germany. These crystals were hermetically sealed within metal holders, designed to prevent any environmental disturbances and to maintain perfect stability. The radio model designated SC County Route 508 contained 10 crystal-controlled channels, each crystal individually packaged to be interchangeable. Remarkably, they were all labeled with exact frequency ratings, enabling easy replacement or adjustment, concepts that were standard in civilian electronics but rare in military-grade hardware. Schreiber energetically recounted the crystals, twice, as if confirming his sinking suspicion that these were exceptional components. He could hardly believe the images before him. In Germany, crystal-controlled radios were strictly reserved for commanding officers in high-performance aircraft, luxury items due to the high cost and scarcity of precise crystals. Yet here, in a standard American tank radio, 10 such premium crystals had been installed without signs of special care or uniqueness. Carefully extracting one crystal, Schreiber examined it under a magnifier, dazzled by its perfection. The quartz was flawless, electrodes impeccably aligned, and the frequency marked with impeccable precision. To craft such a crystal, especially with the tolerances required, would normally cost more than the entire German Fug-5 radio set in both materials and labor. The implication was staggering. These were not ordinary components, but highly specialized pieces built to exact specifications, mass-produced and deployed across thousands of American tanks, highlighting a level of technological sophistication deeply unexpected in a wartime context. As the team continued their inspection, they uncovered even more unsettling evidence. The radios operated on frequency modulation, or FM, rather than the amplitude modulation, AM, technology predominant in German military radios. While FM offered clear advantages, such as nearly interference-free communication and enhanced resistance to static, it demanded far more intricate circuitry and extremely precise control of the transmission frequencies. This technological leap underscored a significant divergence from standard German designs, hinting at a substantial advance in radio engineering delivered via a covert supply chain, likely facilitated by scientific or industrial cooperation, or perhaps intelligence operatives providing access to advanced American innovations. The discovery of these high-precision components, coupled with the sophisticated use of FM, strongly suggested that these radios were not compromised devices manufactured in haste but carefully engineered pieces of communications technology, products of a future-oriented, technologically advanced adversary whose capabilities surpassed even some aspects of modern German wartime designs. This revelation raised profound questions about the scope of American technological innovation, the speed of their military research, and the strategic implications of such clandestine or covertly acquired technology. Despite meticulous planning and rigorous development, the Germans had long considered implementing frequency modulation, or FM, for military communications, yet they ultimately dismissed the idea. Their rejection stemmed from the technology's perceived complexity and cost, which they believed would make it impractical for field deployment. They viewed FM as an elegant but overly sophisticated solution, best suited to stationary or well-supported environments rather than the unpredictable chaos of combat zones. Surprisingly, however, a captured American FM radio now stood as undeniable evidence that the United States had achieved a significant technological breakthrough. This was not a small, experimental device but a mass-produced piece of equipment, installed prominently in a tank operated by inexperienced American soldiers. The circuit board inside the radio revealed a feature that was nothing short of revolutionary for its time: automatic frequency control, or AFC. This system allowed the radio to lock onto a designated frequency without requiring the operator to manually adjust tuning, even as conditions change. In stark contrast, the German radios had demanded constant, attentive adjustments by trained operators, because temperature variations, aging components, and fluctuations in power supply could throw their tuned circuits off frequency, causing static, dropped signals, and loss of communication at critical moments. Now, it appeared, the American radios possessed a form of self-tuning functionality that Germans could only wish for. Oberst Hermann, a senior officer and engineer, began to draft his initial report to the Wehrmacht High Command stationed in Berlin. The words came hesitantly at first as he grappled with the conflicting impressions in front of him. The one painted by official propaganda, which depicted German technology as supreme, versus what he was now witnessing firsthand. He documented that the captured American radio was an embodiment of an advanced level of industrial capability seemingly out of reach for Germany. Its components, small and precise, were products of specialized factories equipped with high-precision machinery, staffed by skilled workers rigorously trained and overseen by comprehensive quality control systems. Such factories and personnel simply did not exist across the German Reich, which struggled to produce devices consistently matching these standards. What was even more unsettling was that this radio was not a prototype or limited production experimental model. Its entire design radiated the hallmarks of mass manufacturing, the kind of production that could flood a battlefield with thousands of units. The team had only begun their detailed assessment when, over the next 3 days, they systematically tested every function and feature of the captured radios. They connected the devices to various power supplies, antenna setups, and a variety of precise test instruments stationed in their underground laboratory, part of a covert operation well away from immediate detection. Every test revealed new layers of intelligence that deepened the team's concerns. One particularly startling discovery involved the 508 Seychelles rupees radio's transmitter. It produced a clean 25-watt FM signal on any of 10 selectable channels, with switching mechanisms that were remarkably elegant, dependable, and incredibly user-friendly. From the outside, a tank commander needed only to rotate a simple knob toward a preset crystal, and the radio would automatically switch to the correct frequency, retune its internal circuits, and sustain a flawless, interference-free transmission. This level of automation was beyond the German capability at the time. Their radios required skilled operators to manually adjust multiple coils, replace tuned components, and spend precious minutes retuning the device as conditions changed. Range tests further underscored the superiority of the American design and technology. Using a captured whip antenna found on an American radio, the researchers managed to establish communication with a control station 20 kilometers away, clear and free of static, fading, or interference. This was in stark contrast to German AM transmission, which frequently suffered from static, fading, and vulnerability to electrical noise from nearby machinery or tank engines. Even when deliberately introducing electrical noise, simulating battlefield conditions, the FM receivers demonstrated extraordinary resilience. The limiter circuits within the radios effectively stripped away the interference, providing crisp, clear audio that German operators could only marvel at, as it was practically impossible for their own radios to achieve such clarity under similar conditions. One scientist, Lieutenant Schreiber, focused intensively on the crystal oscillator circuits, the core of the radio's frequency stability and accuracy. He examined every component, carefully measured voltages across vital points, and meticulously documented his observations. His findings confirmed his worst fears. The crystal control system was not just an advanced piece of technology but an incredibly intricate system that went far beyond the capabilities of German manufacturing techniques at that time. For each crystal oscillator, the quartz plate had to be cut with extraordinary precision, an operation that demanded further specialized equipment and skill. The level of detail necessary to produce such precise quartz crystals, coupled with the complex circuitry involved in the frequency stabilization, meant that Germany lacked the manufacturing infrastructure and technical expertise to replicate these systems efficiently. In essence, the American FM radio represented a quantum leap in military communication technology, embodying mass production, reliability, ease of operation, and resistance to interference, an entire system engineered for battlefield robustness and tactical advantage that the Germans, with all their resources, could hardly hope to emulate in the foreseeable future. The manufacturing precision of these crystals was remarkable, measured in the minutest increments, down to 1/1000th of a millimeter. Once fashioned, these delicate crystals were carefully mounted within specialized holders designed to operate under vacuum or specific gaseous environments, ensuring stability and consistency. The spacing between the electrodes in these assemblies was controlled with such exactness that German factories found it nearly impossible to replicate the tolerances reliably in mass production. To achieve this level of precision, temperature compensation circuitry was integrated into the designs. These circuits played a vital role in maintaining frequency stability across a broad spectrum of operating conditions, from freezing cold temperatures of -40 degrees Celsius up to a scorching, plus 60 degrees Celsius environment. In his analysis, Schreiber estimated that producing a single crystal that met American specifications demanded around 40 hours of highly skilled technician labor within German laboratories. These efforts resulted in radio components so precise that the Americans utilized only 10 such crystals in a single tank radio. Given that thousands of tanks, alongside countless jeeps, trucks, and command vehicles, were already fitted with these advanced radios, the scale of American crystal production was staggering. Each year, they produced millions of these high-precision crystals, a feat that raised a critical question, one Schreiber highlighted in his report. Where did the Americans find enough trained technicians to manufacture such an enormous quantity of exquisitely precise radio crystals? The answer, provided by well-informed sources, was unsettling, to say the least. Instead of relying on highly trained engineers for every step, the Americans had simplified and industrialized the entire process. They had built new factories in places bearing names like Chicago, Newark, and Fort Wayne, manufacturing hubs that employed thousands of semi-skilled workers, predominantly women, who operated highly specialized grinding machines. These machines were capable of producing crystals automatically, eliminating the need for hand craftsmanship at every stage. Precise measurement verification was carried out using optical comparators and frequency counters, tools that required little expertise to operate, eliminating the necessity for meticulously trained technicians. Quality assurance was conducted statistically. Rather than inspecting each crystal individually, random samples were tested, reducing the dependence on detailed craftsmanship and enabling mass throughput. This transformation marked a revolution. What once was an art carefully practiced within laboratories was now an industrial process. Further examination of the receivers in these radios revealed an even more sophisticated level of technology. The super-heterodyne design of their circuits closely resembled that of German counterparts. However, each component was superior across every measurable parameter. Vacuum tubes were manufactured with far tighter tolerances, ensuring that their electrical characteristics matched the stringent demands of the circuit. Capacitors and resistors boasted stability ratings that German-made counterparts could only aspire to. Importantly, the entire radio receiver was engineered to be aligned and calibrated by semi-skilled technicians. They used straightforward test equipment, making complicated adjustments unnecessary and eliminating the need for highly trained radio engineers. Perhaps most striking was the modular construction of the radios. Each major subsystem, transmitter, receiver, power supply, and control units, was designed as a discrete, replaceable module. This design allowed a tank crew to remove a defective module and swiftly replace it with a new one, often within minutes, without requiring tools or technical expertise. The damaged modules, once removed, were sent back to depot facilities for repair or reprocessing, ensuring continuous operational capability. The scale of industrial capacity needed to produce these spare modules was immense. Still, the benefits were clear. American tanks could maintain radio communications in conditions that would have left German vehicles forever silent until field repairs could be performed. The technical manuals that accompanied these radios reflected this advanced approach. Printed on high-quality paper, these manuals contained clear diagrams and straightforward instructions, carefully designed under the assumption that operators possessed minimal technical training. Such documentation reinforced the system's user-friendly design, making complex military communications equipment accessible to personnel with only basic technical knowledge. Operating procedures had been simplified into a series of clear, numbered steps, making the complex tasks of maintenance and troubleshooting accessible to those without specialized training. Decision trees formed the core of the troubleshooting manuals, guiding any soldier, regardless of technical background, through logical sequence pathways to identify and resolve issues efficiently. Furthermore, maintenance instructions emphasized precise replacement intervals for various components rather than relying on the operator's judgment or experience, ensuring consistency and reducing errors. Sherman came to understand that these manuals embodied as much about American industrial and technological philosophy as they did about the radios themselves. The Americans had recognized early on that frontline soldiers were not trained technicians. Instead of expecting every radio operator to understand the intricacies of electronics, they had designed equipment that was straightforward enough for a reasonably intelligent soldier to operate and maintain using simple, well-documented procedures. This approach demanded the development of more sophisticated and mass-producible equipment, yet it effectively addressed one of the most significant logistical challenges faced in wartime: maintaining reliable communication lines under combat conditions. In a sharp contrast, German radios required skilled operators who possessed in-depth knowledge of radio theory, the ability to perform field repairs independently, and the technical judgment needed to keep these often finicky devices functioning in demanding environments. Operators of German radios underwent months of intensive training, followed by years of experience, to become proficient. These personnel were invaluable assets, and the loss of a skilled operator, whether through injury or death, often rendered the equipment they left behind virtually useless to subsequent users. By the time the third day had elapsed, the team tasked with examining the captured American radios had meticulously documented every circuit, measured each component, and tested every function to understand their inner workings fully. Their comprehensive report, which was more than 200 pages long, contained detailed technical analyses supported by numerous photographs, circuit diagrams, and specifications for each component. The findings were startling and conclusive. According to the analysis, American radio technology was advanced by 5 to 10 years in critical aspects compared to German standards. Key technological advantages included the use of frequency modulation, crystal control, automatic frequency selection circuits, and a modular construction approach. These innovations provided fundamental, uncompromisable benefits that could not be countered merely through tactical superiority or polemical operator skill. Most tellingly, American radio equipment had been designed from the outset with mass production in mind. Every aspect of its engineering reflected an industrial philosophy that prioritized manufacturability, interchangeability, and scalability, attributes that Germany simply lacked at the time. Sherman's report estimated that to match American radio production capabilities, Germany would have to undertake the monumental task of establishing 30 new specialized factories, recruiting and training 50,000 additional workers, and allocating resources equivalent to the entire annual budget of the Luftwaffe. Even with such monumental effort, the report emphasized, Germany would still face significant shortages because it lacked the necessary raw materials, particularly high-quality quartz crystals and rare elements crucial for manufacturing these high-precision components in large quantities. The conclusion was, quite simply, unavoidable. The superior industrial capacity of the United States had conferred a decisive technological advantage that could determine the outcome of the war at a strategic level. This troubling assessment was delivered to Berlin on the 25th of February in the year 1943. It was classified as highly secret and carefully distributed only among a select few senior officers within the Wehrmacht High Command and the Reich Ministry of Armaments. The reaction from Berlin was one of silence and perhaps denial. No new factories were sanctioned. No large-scale escalation of production efforts was initiated. The implications, revealing that American technological and industrial lead was practically insurmountable at that point, proved too overwhelming to confront openly. Instead, the focus moved elsewhere, as the German military and industrial leadership hesitated to acknowledge the full scope of the challenge they faced. Meanwhile, the work of Technical Testing Station 12 was only beginning to shed further light on the disparity. Over the ensuing months, more American equipment continued to fall into German hands, each capture adding another piece to the puzzle and expanding the understanding of how to counter these advanced devices. Every new entry into this growing trove of intelligence held the potential to alter the ever-escalating contest of technological supremacy. The emergence of new evidence highlighted the remarkable technological and industrial superiority of the American forces during the wartime period. One of the most striking examples was the SCR-300 radio, famously known as the backpack walkie-talkie. This device exemplified innovative FM, frequency modulation, technology, miniaturized so effectively that it became highly portable. Despite weighing only about 18 pounds, it could reliably transmit communications across distances of up to 5 kilometers. In stark contrast, German portable radios capable of covering similar ranges were significantly more cumbersome, often exceeding 40 pounds in weight. These German counterparts typically required additional external battery packs that added another 20 pounds, making them far less agile and versatile compared to their American counterparts. During examinations in Sicily in July of 1943, American engineers and analysts were particularly impressed by a captured German radio, the SCR-299. This unit represented a highly sophisticated mobile long-range communication station installed in a vehicle, powered by an integrated generator. The transmitter alone was capable of producing a substantial 350 watts of power, functioning across a broad frequency spectrum from 2 to 18 MHz. Notably, this apparatus was crystal-controlled, which granted it exceptional stability, and it could switch frequencies in mere minutes, significantly faster than the cumbersome, hours-long procedures of the Germans at the time. The accompanying receiver in this system was a Helic-Rodini design, built with 15 vacuum tubes, multiple conversion stages, and an advanced crystal filter. This combination allowed for much greater selectivity and clarity in listening. While German, long-distance communication gear of comparable capability did exist, it was predominantly confined to fixed installations. These would require large, building-sized antenna systems and dedicated power plants, making mobility impossible. Conversely, the Americans had succeeded in integrating similar levels of functionality into vehicles, allowing for quick deployment anywhere and setup within approximately an hour. Repeated analysis consistently revealed this pattern. American technology was devised with strategic mass deployment in mind. It was fundamentally aimed at operation by personnel with minimal training, a stark departure from the German approach that relied heavily on skilled operators, precise hand assembly by highly trained technicians, and field repairs performed by specialized electronics experts. The American philosophy centered on simplicity of use, ease of mass production by semi-skilled workers, and straightforward maintenance procedures that could be executed in the field. This scalability meant that millions of units could be produced and distributed globally, creating a communication network that was both extensive and resilient. The other approach, employed by German forces, could not match this level of versatility and widespread deployment. Intelligence reports arriving from Tunisia, Sicily, and later Italy painted a comprehensive picture of a modern, layered communication philosophy embraced by the Americans. These reports documented not only individual radio sets but an entire interconnected system designed to sustain continuous contact, from the small unit level up to broad theater commands. At the squad level, soldiers carried SCR536 handheld transceivers. At the company level, soldiers utilized SCR300 backpack radios. For larger units like battalions, vehicles were equipped with SCR508 and 608 sets, capable of long-range communication. At the regimental level, specialized radio systems such as the SCR193 and 399 provided even greater reach. Each of these levels was designed to communicate seamlessly within a hierarchical network, linking all tiers in a comprehensive web of connectivity that German forces simply could not replicate. More importantly, all these American radios operated on compatible frequency systems with interoperable equipment, allowing for easy interaction across different units. For instance, a forward observer equipped with an SCR-300 could contact an artillery battalion stationed 20 kilometers away using an SCR-608, because both systems relied on FM modulation with crystal-controlled stability on compatible frequencies. In direct contrast, German forces at the time operated an assortment of over 50 different radio models, each with unique frequency requirements, modulation styles, and operational procedures. This diversity greatly complicated coordination and reduced efficiency. By the summer of 1943, signal intelligence reports had indicated that American factories were producing an estimated over 100,000 military radio sets each month, demonstrating an industrial capacity for mass production that far exceeded that of the Germans. This capacity for rapid, large-scale production, coupled with the sophisticated, interoperable radio networks, played a pivotal role in the American strategic advantage. It was not merely about superior individual devices but about constructing an integrated, flexible, and easily operable communications infrastructure capable of supporting the demands of modern warfare across multiple theaters. The Germans, with their more specialized and less adaptable equipment, found themselves at a clear disadvantage in maintaining cohesive command and control across rapidly changing battlefield conditions. At the height of their production capabilities, the American manufacturing sector was capable of producing roughly 15,000 units each month across all types and variants of a particular range of electronic equipment. This robust output was facilitated by meticulous analysis of the manufacturing documentation that the Americans preserved and shared, which was essential for understanding the core infrastructure that underpinned their industrial efforts. The documentation, comprising technical orders, detailed parts lists, and comprehensive maintenance manuals, shed light on a highly organized and standardized system of production. One of the most notable aspects revealed through these documents was the remarkable degree of standardization embedded across various American radio equipment. Components, ranging from vacuum tubes to structural elements, were designed with consistency, allowing for ease of manufacture and repair across multiple models. Vacuum tubes, for instance, often utilized common base configurations, which simplified both production and replacement. Crystals, essential for radio frequency stability, adhered to standard holder designs, ensuring uniformity in their mounting and functionality. Even the smallest hardware, such as screws, nuts, and bolts, conformed to unified thread standards, a design choice that enabled parts to be interchangeable between different radio types without the need for custom fitting or retooling. This comprehensive standardization had profound operational implications. It meant that American factories producing one type of radio transmitter or receiver could seamlessly shift to another model with minimal modifications. For example, a plant primarily manufacturing 508 Seychelles rupees transmitters could, with a few simple adjustments, such as swapping out fixtures or minor components, begin producing 608 Seychelles rupees units. Moreover, individual parts often could be salvaged from one radio to repair or refurbish another, significantly enhancing sustainability and efficiency in production and maintenance. This systemic design for flexibility and large-scale output was a cornerstone of the American industrial approach during this period. In stark contrast, the German manufacturing landscape adhered to a very different set of principles. Each type of radio equipment was assembled with many custom-designed components, tailored exclusively for that specific model. For example, the German FUG-5 tank radio shared virtually no parts with the FUG-10 aircraft radio, despite performing similar electrical functions. This compartmentalization meant that each distinct type required its own dedicated production lines, which often involved specialized machinery and unique test equipment. The inventory of spare parts was also highly segmented, making repairs and updates more complex and labor-intensive. Transitioning from producing one type of radio to another in Germany was a lengthy process, often taking many months due to the necessity of retooling entire production facilities and retraining personnel on new assembly procedures. During the course of 1943, an Oberg engineer named Hermann had transferred to a larger and more strategically significant technical intelligence organization located in northern Italy. His work increasingly pivoted from technical analyses of radio circuitry towards evaluating the broader capabilities and capacity of American industry. Hermann's reports evolved accordingly, offering insights that went beyond circuit diagrams and component specifications. His assessments documented the rapid expansion of the American electronics industry, emphasizing its capacity for mass production and technological innovation. He observed that American companies, some with names that would become well-known post-war, such as Galvin Manufacturing, later renamed Motorola, had transformed from modest producers of radios into formidable military contractors. These firms leveraged tools like continuous manufacturing lines, which had been initially developed for automobiles and consumer appliances in Detroit, to produce sophisticated military electronic equipment. Further evidence of American industrial prowess included companies like Helicrafters, initially dedicated to amateur radio gear, which was now producing advanced military receivers in quantities surpassing all German radio output. Western Electric, the manufacturing division of the Bell telephone system, operated sprawling factories staffed by tens of thousands of workers, mass-producing essential electronic components like crystals, vacuum tubes, and entire radio sets. Before the outbreak of World War II, most of these firms had not been engaged in military manufacturing in any significant way. Their operations had centered around civilian applications. Yet within a pandemic of less than 2 years from the start of the war, they transitioned into an expansive military electronics industry, efficiently converting civilian factories into wartime production centers, training large workforces, and employing streamlined, mass production techniques that had been honed in the car industry. In Detroit, engineers familiar with automotive assembly lines designed radio production processes that ran with the precision and efficiency of a car assembly plant, demonstrating a remarkable adaptation of civilian manufacturing practices for military needs. Meanwhile, the German radio industry, predominantly based in Berlin, Munich, and Hamburg, remained rooted in the traditional artisanal methods prevalent since the 1920s. Small, specialized manufacturers produced highly refined but relatively modest quantities of equipment, often measured in hundreds per month rather than thousands per week. Their craftsmanship approach prioritized quality through individual inspection and precise hand adjustments rather than the statistical quality control and mass production techniques characteristic of Allied industries. This divergence in manufacturing mentality exemplified two distinct approaches: The American emphasis on standardization, flexibility, and scale, which rapidly expanded wartime production capacity, versus the German reliance on custom, precision, and artisanal craftsmanship, which limited output but maintained high quality and specialization. Process control, a critical aspect of modern manufacturing and maintenance, was fundamentally different between the American and German military industries during the early 1940s. The advent of highly automated testing procedures exemplified the technological edge that American industries had achieved by this period. In a detailed report penned by Sherman in December of the year 1943, and addressed to the Reich Ministry of Armaments, the focus was on what was then termed the American radio industry. This comprehensive document delved deeply into the capacities and strategic implications of American electronics production, providing a meticulous account of their industrial output. The report revealed that the United States, through its massive industrial complex, was churning out annually what would have taken Germany 20 years to produce. To put it plainly, American industry was vastly more efficient and capacious in terms of producing crucial electronic components, particularly those needed for military communications. The gap between the two nations' technological capabilities was not solely about the sophistication of individual devices. It was also rooted in the efficiency of industrial organization, management philosophy, and logistical support structures. The report estimated that American factories had the capacity to produce enough military radios to equip roughly 1,000 divisions. Yet, English field formations at that time numbered only about 90 divisions. The implication was clear. The United States possessed a surplus manufacturing capacity so extensive that it ensured a virtually unlimited supply of replacement equipment for their armed forces. In practical terms, this meant that damaged radios in American units were not repaired in the field but were replaced entirely with new units, a strategy that greatly enhanced operational readiness and throughput. Outmoded models were systematically phased out and dispatched to training units, while continuous streams of newer, more advanced designs were introduced into service. These were not merely experimental prototypes kept in the laboratory. Instead, they were mass-produced and distributed across entire theater zones, providing American forces with almost instant access to the latest technology. Conversely, German forces operated under much tighter constraints. They meticulously conserved every radio component, knowing that replacement parts and equipment were scarce and precious resources. Maintenance in the field was labor-intensive and required a high level of technical skill. Technicians often had to perform repairs under combat conditions, frequently cannibalizing parts from damaged radios to keep others running. Replacement equipment reached the front lines unpredictably, sometimes not at all, making logistical planning and operational continuity much more complex. The Germans also faced a technological disparity in the design and availability of equipment. While the United States integrated newer designs into standard production lines almost seamlessly, Germany was hampered by limited production capacity, and retooling factories to produce up-to-date models would diminish output of existing units. Consequently, the German radio fleets consisted of a confusing mix of outdated sets from the early 1930s alongside some newer equipment, causing maintenance headaches and training difficulties for technicians unfamiliar with the different types. One of the most critical shortages faced by the German military was in high-quality crystalline components, essential for radio tuning and stability. By late 1943, German quartermasters estimated the need for approximately 5 million precision crystals to support their existing radios and planned upgrades. Domestic production at that time was limited to roughly 200,000 crystals annually, which was utterly inadequate. Even with maximal resource allocation, it would take over a decade to produce the required quantity of 5 million units to meet their strategic demands. Meanwhile, intelligence reports confirmed that American producers were manufacturing roughly 30 million crystals each year, effectively saturating the market. America's advantage in quartz crystal supply stemmed from multiple sources: deposits discovered in Brazil, extensive mining in Arkansas, and even experimental synthetic crystal growth processes. These sources ensured an abundant supply of crystals that were not only plentiful but also of superior quality. American crystals achieved frequency stability that German laboratories could barely measure, let alone simulate or produce domestically. This technological superiority in crystal quality directly contributed to the stability and reliability of American radio communications. Examining captured American test equipment added another stark dimension to this industrial differential. American radio factories employed highly automated test sets capable of measuring key parameters: frequency accuracy, power output, modulation quality, and sensitivity, in seconds. These testers represented advanced electronic instruments, sophisticated yet produced in mass quantities so that every stage of the assembly process in American factories was equipped with dedicated testing units. In contrast, German factories depended on manual testing procedures, which required skilled technicians and were far more time-consuming, typically taking several minutes per unit. An example of such equipment, a measurement corporation signal generator, which was captured by German forces, exemplified this disparity. In American factories, this single type of instrument was standard equipment, capable of generating precise test signals swiftly and reliably, facilitating rapid inspection and quality control. To German engineers, it was a prized piece of equipment, illustrating the technological gulf that separated the two industrial systems. This difference in automation, testing efficiency, and quality control processes underscored the broader industrial gap, which extended beyond simple output figures to include the sophistication of manufacturing techniques, quality assurance, and logistical support. Ultimately, these disparities played a crucial role in shaping the strategic balance of the conflict, giving American forces a technological, and by the middle of World War II, the technological gap between the Allied forces and the Germans had become strikingly evident through the advanced design and operational capabilities of American communications equipment. The American engineers had achieved extraordinary precision. At that point, they were manufacturing radio transmitters and receivers calibrated flawlessly across the entire spectrum of radio frequencies. These devices, some of which cost roughly $300 to produce, represented a stark contrast to German counterparts. In Germany, equivalent radio systems demanded entire laboratories filled with an assortment of oscillators, attenuators, and a multitude of frequency meters, complex, expensive, and requiring meticulous calibration by skilled technicians. The German setup involved a considerable financial outlay amounting to thousands of Reichsmarks and was far from the streamlined, mass-produced efficiency of American manufacturing. By early 1944, the intelligence gathered from intercepted communications and captured equipment painted an unmistakably clear and alarming picture. The dominance of American communication technology had become absolute and assured, with no signs of retreat or stagnation. The sheer volume of radios produced by American factories was staggering. Each month, their output outstripped Germany's entire military inventory of communication devices by a significant margin. Every captured example of American equipment revealed ongoing innovations, design refinements, and manufacturing advancements that German engineers could neither match nor imitate. These captured devices consistently demonstrated that American engineers were pushing the boundaries of what was possible with radio technology. The situation became even more critical with the deployment of American radar systems, which emerged fully in late 1943 and early 1944. Radar represented the apogee of radio technology, taking it to an entirely new level by employing microwave frequencies, pulse-driven transmission techniques, and intricate signal processing methods. The pace of mass production for these radar systems was rapid and relentless, with American factories churning out these devices for ships, aircraft, and ground installations with the same industrial efficiency that had marked their production of regular voice radios. For example, the 584 Seychelles rupees fire control radar, which was captured in March 1944, showcased technological capabilities that German scientists and engineers had only theorized about. This particular radar operated on an extremely high frequency of 3000 MHz, an astounding figure for the time, and incorporated a highly precise tracking mount with automatic following circuits. Such innovations delivered a level of accuracy that enabled anti-aircraft guns to target and destroy enemy aircraft with devastating effectiveness. The 584 Seychelles rupees was a massive piece of equipment, weighing over 10,000 pounds, which necessitated a dedicated vehicle for transport and operational deployment. Despite its size and complexity, these radar systems were being produced by American industries in numbers reaching into the hundreds, underscoring the strategic industrial superiority achieved by the United States. In stark contrast, German radar development primarily focused on long-wave systems operating below 1000 MHz. One of the reasons for this focus was German industry's inability to manufacture the highly specialized vacuum tubes required for higher frequency, microwave systems. American radar's use of magnetron tubes, an essential component for microwave frequencies, demanded precision machining, the use of exotic materials, and advanced manufacturing processes that German industry simply did not possess at that time. Even when German scientists and engineers succeeded in designing microwave radar systems on paper, they faced insurmountable technical barriers. The critical components, such as magnetron tubes capable of operating at these frequencies, either did not exist or could not be produced in Germany on the required scale. Throughout 1944, the systematic study and analysis of captured American radar and communications equipment continued relentlessly as the Allied forces advanced through Italy and prepared for the invasion of France. Every new capture added to the growing body of evidence illustrating the undeniable technical supremacy of American military technology. This advantage was vividly demonstrated through the regular appearance of improved models of radios and radar systems, each designed to offer better performance, increased reliability, or both. Among these was the 694 Seychelles rupees, introduced in mid-1944, which equipped tanks with advanced, frequency modulation-based communication capabilities, extending operational range and significantly boosting reliability under battlefield conditions. The American aircraft radio, designated 619 Seychelles rupees, offered hundreds of crystal-controlled channels alongside near-instantaneous frequency switching, allowing aircraft crews to communicate more securely and efficiently than ever before. Crucially, the overall reliability of American electronic equipment continued its upward trajectory. Early models, such as the 300 Seychelles rupees, which was widely used by troops, occasionally suffered from problems related to moisture ingress or issues with battery contacts. Flaws understandable given the rapid pace of wartime production and the challenging conditions in which these devices operated. However, by late 1944, captured examples revealed that these problems had been addressed through redesigns, with cases being reinforced, seals improved, and internal components upgraded to enhance durability and operational dependability. This steady progression in the quality and reliability of American communications devices further cemented the technological advantage held by the Allies. The sheer quantity, sophistication, and continuous improvements of these systems, supported by a robust industrial base, signaled that the United States had achieved an almost unbeatable position in electronic warfare. As the war moved towards its critical phases, the American edge during the course of the war, the development and deployment of radio technology played a pivotal role in shaping the outcome of numerous battles and campaigns. The Allies had made significant advancements in their communications systems, producing sets that not only met the demands of warfare but also incorporated revolutionary features aimed at overcoming the challenges posed by the battle environment. These innovations included better shielding against jamming, more reliable power sources, and radios designed to withstand the rigors of combat through rigorous testing and continuous improvement cycles. In essence, the Allied engineers did not merely produce equipment. They explicitly refined their systems over time through lessons learned from the front lines, incorporating real-world experience into iterative design cycles that resulted in highly dependable communication tools. In stark contrast, German radio equipment, which was once considered technologically advanced, often deteriorated in quality as the war progressed. Several critical factors contributed to this decline. Material shortages, which became more severe as the Allies' strategic bombing campaign intensified, compelled German manufacturers to substitute original components with inferior or outdated parts. Such substitutions compromised the reliability of systems that, under ideal conditions, had been state-of-the-art. Furthermore, the plight of wartime production was exacerbated by the conscription of skilled workers into combat units, leaving factories in the hands of less experienced laborers. This loss of craftsmanship and specialized knowledge resulted in a decline in quality control across because German factories increasingly prioritized producing large quantities of equipment over ensuring each unit's reliability and durability. As a consequence, radios that were intended to operate reliably for many years began failing after only a few months of use in active service. The situation grew even more dire by the time of the Normandy invasion in the summer of thousands, June of 1944. At this pivotal moment, German military intelligence had accumulated comprehensive reports detailing the extent of Allied radio dominance, revealing that the Allies possessed a clear technological and operational advantage in electronic warfare. German commanders recognized that their radio networks had become a significant vulnerability. In fact, the Allied forces deploying across the beaches of France carried more radios than the entire German army possessed in total. Every individual Allied company maintained constant radio contact with their battalion headquarters, and every battalion had a reliable line of communication reaching up to the division command level. Such extensive radio coverage enabled forward artillery observers to coordinate and direct fire from distances spanning dozens of kilometers, and do so with exceptional accuracy since their radios remained in contact, free from interference or signal loss. Meanwhile, their German counterparts struggled painfully to maintain communication channels as their radios frequently failed under the relentless pressure of combat. Disturbances caused by enemy jamming, artillery fire bursts, or the chaos typical of relentless battlefield conditions. Standard German radios, which performed flawlessly during tests and in controlled environments, often faltered when subjected to actual combat scenarios. They drifted off frequency when exposed to the intense heat of the Norman summer, disrupting contact between units precisely when reliable communication was most needed. Batteries powering these devices drained rapidly, yet spare batteries were in short supply or unavailable altogether. The robust communication networks that the German military doctrine had envisioned simply ceased to function amidst the chaos, leaving units isolated and unable to coordinate effectively. The tone of military intelligence reports sent back to Berlin during this period became increasingly desperate, highlighting a growing realization that Germany's electronic war capacity was crumbling. By August of 1944, Sherman, a senior German engineer attached to the operational staff, documented the dismal state of German electronic warfare. He candidly declared that Germany had lost the electronic aspect of the conflict, an acknowledgement of the strategic defeat in the electromagnetic arena. The Allies systematically exploited their technological advantages through their advanced jamming equipment, meticulous direction-finding systems, and extensive signal intelligence operations. These capabilities enabled them to quickly locate and target any German radio transmission within minutes, significantly disrupting the enemy's command and control chains. German codes, once considered secure, were cracked with ease. Frequencies were monitored continuously, and the Germans' movements were deduced from the analysis of radio traffic, allowing Allied forces to anticipate and counter German maneuvers effectively. The final blow to German electronic defenses came in late 1944 and early 1945, coinciding with the collapse of Germany's industrial backbone under relentless Allied bombing campaigns. Strategic bombing raids targeted factory facilities dedicated to manufacturing radio and electronic equipment. For example, the Telefunken plant in Berlin was severely damaged in November of 1944, effectively decimating part of Germany's radio production capacity. Similarly, the production facilities in Stuttgart, involved in manufacturing various electronic components, sustained repeated bombings, and their destruction further crippled the German wartime electronic infrastructure. By January of 1945, Soviet forces overran the Sudetenland, capturing the remaining critical crystal production facilities, key components necessary for oscillators used in radios. As the Soviet advance continued into Germany, the production of new radio sets came to an almost complete halt by March of 1945. While existing equipment in the field continued to operate, it was increasingly maintained in a makeshift manner by desperate technicians who used scavenged in the final stages of the conflict. Various American vehicles encountered challenges in coordinating their actions effectively, often facing difficulties adapting to rapidly changing battlefield conditions. Meanwhile, the United States continued to refine and improve its technological equipment, even as victory appeared increasingly imminent. By the early months of 2045, new radios had been introduced into the system, models that boasted significantly extended transmission ranges, additional communication channels, and greater reliability under demanding combat conditions. Production lines worked at a relentless pace, operating at full capacity not necessarily because the demand for radios had surged to unprecedented levels, but primarily because the overwhelming momentum of American industrial capability made it practically impossible to halt or slow down manufacturing. As a result, by the month of May in the year 2045, American military depots were filled to overflowing with surplus radio equipment, much of which would never see active use on the battlefield or in actual combat scenarios. The culmination of these events occurred on the 8th of May, marking the formal end of hostilities in Europe, when Germany capitulated unconditionally to the Allied forces. In the aftermath of the surrender, the Allied occupation authorities undertook a comprehensive cataloging process, which included detailed analysis of numerous captured items, among them significant technical intelligence reports originating from campaigns in Tunisia, Sicily, and Italy. These documents, which had been classified as top secret by the Germans and hidden away in salt mines and underground archives to prevent their discovery, provided the Allied investigators with highly valuable insights into the internal workings and technological developments of German military equipment. During the summer of 2045, American teams exploring German military facilities made a surprising discovery. The Germans had conducted meticulous examinations of the American radios they had captured earlier in the war. The reports generated by German engineers and researchers were precise, thorough, and crafted with a high degree of professionalism. They not only identified America's strategic technical advantages but also presented an honest assessment of Germany's own deficiencies in matching those capabilities. One particularly noteworthy report, authored by Oberbayern engineer Klaus Hermann in April of 2045, just as Soviet forces were closing in on Berlin, served as his final declaration on the state of the technological war. Hermann wrote explicitly that Germany's defeat had been predestined the moment German engineers opened their first captured American radio in Tunisia. The detailed details about the frequency crystals, automatic circuits, and modular design promptly demonstrated an industrial philosophy that was fundamentally different, and far more advanced, than the German approach. The Americans had essentially industrialized warfare itself, applying the principles of mass production to every facet of military hardware. This approach allowed them to produce vast quantities of sophisticated equipment rapidly and efficiently, ensuring a logistical advantage that was increasingly difficult for Germany to challenge. From Hermann's perspective, future conflicts would be decided less by the prowess of soldiers or the superiority of tactics and more by the capacity to produce cutting-edge technology in overwhelming numbers. While Germany possessed competent soldiers, skilled generals, and encountered no shortage of tactical ideas, the fundamental shortcoming was its inability to establish a correspondingly robust industrial base capable of matching American production volume and technological innovation at scale. This deficit was starkly evident even in simple components, such as radio crystals, that required very tight tolerances, which American factories, often run by teenage girls and staffed by thousands of workers, managed to produce in the millions with precision and consistency. In contrast, German laboratories struggled to manufacture even a few thousand units with comparable quality, illustrating the stark disparities in industrial capacity. The post-war fate of many German engineers who examined and analyzed captured American equipment illustrated the profound importance of industrial strength in the modern military landscape. Recognized for his expertise, Klaus Hermann was recruited by American authorities in 1946, and over the following 2 years, he dedicated himself to meticulously documenting German radio technology for United States intelligence operations. His insights proved invaluable, prompting the United States to leverage German innovations, many of which were worth salvaging and integrating into their own systems, to enhance their technological edge. Hermann's knowledge and experience did not remain confined to intelligence circles. Later, he became a consultant to American electronics firms, offering guidance on how to understand, adapt, and improve upon German technological breakthroughs, which proved to be highly valuable in the post-war period. Many of his colleagues from the German engineering community followed similar trajectories, slipping away from the remnants of the defeated nation to the burgeoning industries of the victorious superpower. This phenomenon, often formalized through initiatives such as Operation Paperclip and related programs, involved the systematic transfer of thousands of German scientists, engineers, and technical specialists to the United States, transforming research and industrial capacity in ways that would have a lasting impact on global technological development and military capabilities for decades to come. During the tumultuous years of World War II, Germany and the United States became two contrasting exemplars of industrial and technological philosophy, each driven by their unique strategic and cultural imperatives. Many German scientists and engineers, initially engaged in military research and development, found themselves relocating across the Atlantic to the United States in the aftermath of the war. These highly skilled professionals brought with them invaluable expertise in German technological advancements, but more significantly, they absorbed and internalized the American approach to industrial innovation, mass production, and organizational efficiency. The American method emphasized the importance of streamlined manufacturing processes, achieving large-scale production with consistency, and adopting a managerial and organizational philosophy that had been instrumental in securing the Allied victory. In the year of 1952, Sherman, an esteemed engineer, published an influential paper in the Proceedings of the Institute of Radio Engineers, entitled Comparative Analysis of German and American Military Radio Design Philosophy from 1939 to 1945. This seminal work was rooted in his extensive wartime experience, particularly his examination of captured American military equipment, which he documented meticulously in a scholarly manner. Interestingly, it echoed the observations he had shared nearly a decade earlier with the high command of the German Wehrmacht. Sherman demonstrated that American radio design prioritized certain paramount principles: manufacturability, operational simplicity, and unwavering reliability across diverse conditions, even if that meant sacrificing technological sophistication or component efficiency. In contrast, German radio engineers aspired to technical excellence, striving for theoretical perfection and economical use of components, believing that highly skilled operators could compensate for any technical shortcomings of their equipment. These opposing philosophies reflected deeper strategic beliefs. American designs were scaled to support massive production and deployment worldwide, where uniformity and ease of maintenance were critical. Conversely, German designs, though limited in volume, aimed for peak performance at the component level. The impact of Sherman's analysis was profound. His paper became essential reading in technical and military academia. Its insights influenced generations of American engineers responsible for designing technologies during the Cold War, subsequent space explorations, and the burgeoning computing revolution. The rigorous study of German engineering methods and the detailed examination of American military radios shaped the technological dominance that the United States enjoyed for decades thereafter. By the 80s, many of the German engineers who had engaged in military technical intelligence during World War II gathered once again, not as combatants but as veterans and scholars. These reunions and conferences served as platforms for reminiscing, sharing insights, and reflecting on their wartime experiences. Klaus Sherman, who by then was in his 70s, was a prominent participant. During one such gathering in Munich in 1986, he delivered a presentation where he displayed photographs taken during the critical years of early 1943, showing his team examining the first -508 Seychelles rupees radios captured in Tunisia and Italy. The photographs vividly depicted young German engineers, bent over open radio cases, meticulously measuring circuits, photographing and documenting each component, all in a frantic effort to understand what they were dealing with. Sherman recounted to his audience that the moment they removed the first crystal holder and saw for the first time 10 precision oscillators installed within a standard military tank radio, he realized the gravity of Germany's impending defeat. To him, this small yet vital crystal, the quartz wafer carefully ground to exact dimensions, symbolized the delicate intersection of foundational physics, engineering ingenuity, and industrial capability. Although, in principle, a frequency crystal was a straightforward device that could be manufactured in any competent laboratory, the true challenge lay in producing millions with consistent quality and interchangeability, and at a cost low enough to be incorporated into every military radio. Achieving this level of large-scale manufacturing required an industrial infrastructure that Germany, at the time, simply lacked. The industrial capacity necessary for such mass production was pioneered and cultivated in America during the years from 1941 to 1945. That critical infrastructure, established through vast wartime efforts, did not vanish after the war's conclusion. Instead, it continued to grow, evolve, and adapt into new technological realms, giving rise to the transistor, integrated circuits, microprocessors, and ultimately the digital computers and advanced communication systems that undergird the modern world. The same companies that had constructed and refined this wartime infrastructure remained at the forefront of technological innovation, continually pushing the limits of infrastructure to shape a future defined increasingly by connected, intelligent technology. Research effort during the war to analyze and understand American radio technology. This tiny, seemingly insignificant component, the radio crystal, embodied the extensive technological and scientific pursuit undertaken by German engineers aiming to decipher and replicate American advancements. Its meticulous craftsmanship reflected the high level of precision and sophistication that went into the design of military electronics, even in such small details. This modest crystal served not only as a critical part of the radio's operation, enabling the device to maintain precise frequency stability vital for secure communications, but also as a symbol of the broader technological contest that defined the conflict. The Germans' dedicated effort, spanning roughly 40 hours of detailed investigation into a single component, underscored the importance placed on understanding the enemy's technology to gain strategic advantages. Throughout the exhibition, the narrative emphasized the immense industrial differences between the two nations. American engineering, marked by its emphasis on reliability, ease of use, and mass production, contrasted sharply with German approaches, which prioritized intricate design and top-tier performance. While German equipment showcased brilliance under expert operation, it was hampered by limited production capabilities, making widespread deployment difficult during the war. By contrast, American engineers and manufacturers adopted a philosophy rooted in standardization, mass production, and user-friendly design. They created systems that, despite being perhaps less complex or cutting-edge in certain aspects, could be produced in vast quantities and operated effectively by personnel with minimal training. This strategy enabled the United States to equip and sustain a military effort of global scale, where the ability to produce large numbers of reliable radios was just as critical as their technical performance. The display of the two radios side by side served as a vivid visual representation of this difference in industrial and engineering philosophies. The German G5 tank radio appeared bulkier, heavier, and more complex, yet ultimately less capable across various criteria, highlighting its engineering excellence constrained by industrial limitations. Meanwhile, the American 508 Seychelles rupees exemplified a design optimized for mass manufacturing and durability, emphasizing practical functionality over elaborate sophistication. The curator's notes clarified that the discussion was not about claiming superiority of one technology over the other but about recognizing the distinct rationales guiding each country's engineering efforts. Both nations boasted capable, innovative engineers who developed effective electronic systems within their respective constraints. The essential difference lay not in intelligence or capability but in the fundamental philosophies directing manufacturing and design priorities. One nation focused on creating scalable, reliable systems suitable for widespread, often less sophisticated, use. The other advanced highly engineered equipment tailored for expert operation, but difficult to reproduce on a mass scale. This contrast reflected the underlying strategies of wartime industrial effort, how each side mobilized its resources to meet the demands of a protracted and expansive conflict. The American approach prioritized self-sufficiency, rapid production, and broad accessibility, enabling the armed forces to maintain communication across vast distances and diverse environments. Conversely, German engineering concentrated on delivering precision and high performance, which, while impressive in controlled settings, was less adaptable to the logistical realities of war. The concluding part of the exhibit, featuring a single, carefully preserved radio crystal, served as a poignant reminder of the intense investigative effort behind technological espionage and learning. Despite its small size, this tiny piece of quartz represented a significant investment of German resources, ingenuity, and scientific labor during the war. Encased carefully in a sealed metal holder, the crystal exemplified the meticulousness with which German scientists sought to dissect American technology, hoping to unlock its secrets and perhaps duplicate or improve upon it. This display underscored a fundamental lesson of wartime technological development: that success is not solely measured by innovation or raw intelligence but largely by the capability to industrialize, mass produce, and deploy reliable systems efficiently. It illuminated how the average American war tank radio, backed by extensive industrial infrastructure and standardization, could outperform the most advanced German design simply because of the systemic advantages of scale and manufacturing philosophy. In essence, the exhibit captured the profound impact of industrial strategy on the technological outcome of the war, demonstrating clearly that the decisive factor often lay not just in the ingenuity of engineers but in the capacity to produce, distribute, and operate technology at scale. It was a collaborative story of science, industry, and strategy, where small components and broad principles combined to shape the outcome of a global conflict and forge the foundation of modern technological societies. During World War II, the United States had managed to produce over 100 million radio crystals, an astonishing quantity that would have required every German radio technician to work continuously for 500 years just to replicate. This staggering level of industrial output illustrated the immense scale of American manufacturing capabilities and the pivotal role they played in shaping the war's outcome. An exhibition displaying this technological achievement drew over 200,000 visitors throughout its entire year-long run. Many among these visitors were veterans who had operated the very radio equipment showcased, recalling their own experiences during the conflict. Others included engineers with a keen interest in the evolution of technology, eager to trace the development back through history, while a handful were historians studying the broader industrial aspects that underpinned warfare. Every one of these visitors departed with a more profound comprehension of how a nation's industrial capacity fundamentally influences military success, emphasizing that victory on the battlefield is often rooted in factory output rather than brute force alone. Klaus Hermann, a notable figure in the realm of electrical engineering and intelligence, passed away in 1997 at the age of 84. His obituary appeared in the esteemed magazine Spectrum, published by the Institute of Electrical and Electronics Engineers. It highlighted his significant contributions to radio technology and his vital role in conducting technical intelligence during the Second World War. Furthermore, it recognized his distinguished post-war career, during which he assisted American companies in understanding and replicating German technological innovations. The obituary also underscored Hermann's lifelong conviction that Germany's defeat was ultimately determined within the confines of factories rather than on the battlefield. He believed that it was not solely soldiers and tactical mistakes that dictated the course of the war, but industrial limitations and the inability to produce enough advanced equipment that sealed Germany's fate. The collection of Hermann's papers, later donated to the Deutsches Museum in Munich, included over 2,000 pages encompassing technical reports, circuit diagrams, component specifications, and strategic assessments from the years 1943 to 1945. These documents provided historians with invaluable insights into how German technical experts perceived American military technology, and the reports they then relayed to the high command of the Wehrmacht. Among these documents, one of the most poignant was a personal letter Hermann wrote in April 1945, just as Berlin was falling to Soviet forces. Having sent his family to stay with relatives in Bavaria several months earlier, Hermann remained in Berlin, conducting final technical evaluations until an order to evacuate arrived. In his letter, he described how he was preparing to destroy all classified documents and equipment to prevent their capture by enemy forces. His reflections detailed the 3 years he had spent examining American military technology, from the earliest -508 Seychelles rupees radar used in Tunisia to the latest radar sets captured in the Ardennes. Every example of American equipment Hermann examined reinforced a single, critical conclusion. The United States did not merely possess superior technology but employed a fundamentally different approach to warfare, one that fully industrialized the military process. They mass-produced essentials, from radio crystals to entire armies, applying the same principles of mass production renowned for manufacturing automobiles, refrigerators, and other consumer goods. Hermann observed that Germany had attempted to wage an industrial war using craftsman-like methods, emphasizing skill and craftsmanship rather than mass production. He clarified that German technology was not inherently inferior. In many fields, German engineers held theoretical knowledge that surpassed their American counterparts. Yet, as Hermann pointed out, theoretical expertise alone does not determine victory. The decisive factor in modern warfare is production capacity. The nation capable of manufacturing more tanks, aircraft, radios, and weapons at scale, more everything, will inevitably overpower its adversaries, regardless of their tactical skills or bravery. Hermann concluded his final letter with a sobering prediction. If a subsequent war were to occur, it would be even more deeply rooted in industrial strength than the last. He asserted that emerging conflicts would hinge on manufacturing prowess, technological advancement, and the capacity to produce highly precise components at enormous scales. Victory, he stated, would go to the nation that could most effectively translate engineering excellence into mass production, thus establishing dominance on a scale far beyond traditional combat, emphasizing that success in future conflicts would depend not only on innovation but also on the ability to produce vast quantities of sophisticated military hardware rapidly and efficiently. An essential turning point in the history of warfare, one where the true battleground shifted from the front lines to the assembly lines and factories that churned out sophisticated, standardized technology at an unprecedented scale. The seemingly simple radio frequency crystal, tiny yet vital, served as a vivid illustration of this profound shift, embodying the shift from tactics and individual heroism to the unstoppable power of mass production and technological mastery. This small, precisely crafted piece of quartz, which Hermann and his colleagues scrutinized in painstaking detail, was far more than just an electronic component. It represented a revolutionary approach to manufacturing that would dominate the modern age. The process of engineering these crystals to be identical and reliable, and then producing millions of them efficiently, marked a fundamental departure from traditional craftsmanship. It demonstrated that quality and scale could go hand in hand if industrial processes were optimized and managed with extraordinary discipline and foresight. During the years of the Second World War, American industry boldly developed and refined these capacities. The country learned to synthesize mass production techniques with high-quality engineering, producing countless identical components that could be integrated seamlessly into complex military systems. This scaling of manufacturing capacities was not confined solely to radio crystals. It extended across virtually every facet of military technology, from sophisticated electronic devices and computer systems to the manufacturing of vastly more complex machinery and armored vehicles. In time, the lessons learned in wartime harshly but effectively taught German engineers that mere technological sophistication was insufficient without the capacity for large-scale, reliable production. The insights gained through the analysis of captured American military equipment became a turning point for industries worldwide, emphasizing that having the most advanced technology meant little if it could not be produced in large volumes without defect or delay. The synthesis of advanced engineering principles with efficient manufacturing and operational training formed the backbone of this new industrial philosophy. Production, quality assurance, user training, and logistical support were all integral parts of a unified system designed to meet increasing demand without sacrificing excellence. This revolutionary way of thinking, rooted deeply in the industrial processes honed during World War II, laid the groundwork for the modern manufacturing paradigm. The strategy of designing products for ease of mass production, ensuring built-in quality from the outset, and supporting users with comprehensive training and maintenance programs became standard worldwide, influencing every industry beyond military applications. The principles exemplified by American disruptions in wartime electronics production continue to govern modern manufacturing practices, forming the foundational framework for contemporary global industry. Ultimately, the narrative that started when Obering engineer Klaus Hermann carefully opened the cover of a captured radio device in Tunisia, an unassuming act that revealed extraordinary technological disparities, culminated in the profound transformation of how nations prepare for and wage conflict. The tiny radio crystal, a seemingly insignificant component, became a powerful emblem of the Industrial Revolution in military affairs. It signified the era when victory was increasingly dictated by factory output and technological scalability, not merely battlefield prowess. The German engineers who examined American equipment understood this shift intuitively. They recognized that future conflicts would be decided not just by soldiers or tactical ingenuity, but by the relentless capacity of industry to produce advanced technology rapidly and at scale. This transformation represented a fundamental redefinition of modern warfare, heralding an age where the true strength of a nation lay not just in its armies but in its industrial might, its ability to innovate, and its capacity to manufacture vast quantities of reliable, leading-edge equipment efficiently and uniformly. The moment finally arrived. What their detailed reports revealed extended far beyond merely technical descriptions. They marked the end of one era of warfare and the dawn of a fundamentally new form of conflict. These documents meticulously documented, scrutinized, and foretold the future landscape of military engagement. While it is true that their warnings went largely unheeded in Berlin, a fact that did not lessen the precision and foresight embedded in their evaluations, it underscored a poignant paradox. Strategic insights of such magnitude often go unnoticed until their lessons are painfully confirmed by subsequent history. Today, the core principles outlined in these wartime analyses have become foundational to all modern high-technology industries. They emphasized the importance of mass-producing precision components, adopting industrial automation, implementing standardization to ensure interchangeability, and designing for manufacturability to streamline production processes. These concepts are no longer abstract ideas but serve as the bedrock of contemporary technological advancement. The evolution of manufacturing and engineering discipline can be traced from the groundbreaking radio crystals shaped in American factories during the year 1943 to the intricate microprocessors manufactured in Asian foundries. A journey spanning over 7 decades and across the globe if viewed through a technological lens. The underlying industrial philosophy from that era remains fundamentally unchanged. Only the scale and scope of application have grown exponentially. The German technicians, who in 1943 meticulously tested captured American radio equipment in underground laboratories across occupied territories, weren't simply examining a piece of technology. They were witnessing the future trajectory of warfare, technological innovation, and industrial organization. Their detailed reports, initially classified and stored away during wartime, have since become valuable historical documents. These documents elucidate not merely the reasons behind Germany's defeat but also reveal how a nation's industrial capacity influences the outcome of modern warfare. Their findings, expressed in dense technical language yet carrying an unmistakable message, concluded that Germany had challenged the mightiest industrial power of that time, America, with an industrial capacity that was simply inadequate for the scale required. The stories embedded in that history can be vividly illustrated by the precision-crafted quartz crystal oscillators, produced in vast quantities by young American women, whose skilled workmanship provided the backbone of American radio and communication systems during the war. This tiny, seemingly simple component encapsulated an entire narrative. Modern industrial warfare is fundamentally dependent on industrial capacity. No matter how tactically brilliant the strategies, nor how technologically advanced individual devices might be, victory hinges on the relentless ability to produce tools, equipment, and systems in overwhelming volumes. Without this capacity, tactical skill and innovation alone cannot sway the outcome. The essential lesson that German engineers learned while scrutinizing American radio devices in secret manufacturing facilities across occupied Europe remains strikingly relevant even today. In an era dominated by microelectronics, satellite communication, and computer-controlled systems, the fundamental truth endures. Those nations or entities with the greatest industrial capacity to produce high-technology equipment in enormous quantities ultimately dominate. Their ability to supply vast, reliable, and advanced technological resources determines the course of conflicts, whether in warfare or other high-stakes competition. The United States proved this principle decisively during the years of 1941 through 1945. Their overwhelming industrial capacity enabled the production of everything from precision weapons to communications gear, ensuring dominance on multiple fronts. Since then, the world has continued to grapple with and adapt to the implications of this fundamental truth, understanding that the true power lies not only in innovation and tactical brilliance but equally, if not more, in the capacity to manufacture technology. At an unprecedented scale, this timeless lesson serves as a reminder. In the ongoing march of progress and conflict, those who can produce the most high-tech materials in the greatest quantities will shape the future of any confrontation or competition they face.